Hi everyone, this is Glenda Ganzon and welcome to my Human Anatomy and Physiology class. And for today's lesson, I'm going to discuss the chemical bonds. Atoms separated by a great distance cannot link. Rather, they must come close enough for the electrons in their valence shell to interact. But do atoms ever actually touch one another? The answer is no, because the negatively charged electrons in their valence shell repel one another. No force within the human body or anywhere in the natural world is strong enough to overcome the electrical repulsion. So when you read about atoms linking together or colliding, bear in mind that the atoms are not merging in a physical sense. Instead, atoms link by forming a chemical bond. So, what is a bond? A bond is a weak or strong electrical attraction that holds atoms in the same vicinity. The new grouping is typically more stable or less likely to react again than its component atoms were when they were separate. A more or less stable grouping of two or more atoms held together by chemical bonds is called molecule. The bonded atoms may be of the same element as in the case of hydrogen, which is called molecular hydrogen or hydrogen gas. When molecule is made up of two or more atoms of different elements, it is called chemical compound. Thus, a unit of water is a compound as a single molecule of gas, methane, or CH4. There are three types of chemical bonds that are important in human physiology because they hold together substances that are used by the body for critical aspects of homeostasis, signaling, and energy production, to name just a few important processes. These are: number one, ionic bonds. The second is covalent bonds. And the third is the hydrogen bonds. Let me discuss to you the first one, which is the ions and the ionic bonds. Recall that an atom typically has the same number of positively charged protons and negatively charged electrons. As long as this situation remains, the atom is electrically neutral. But when an atom participates in a chemical reaction that results in the donation or acceptance of one or more electrons, the atom will then become positively or negatively charged. This happens frequently for most atoms in order to have a full valence shell. This can happen either by gaining electrons to fill a shell that is more than half full, or by giving away electrons to empty a shell that is less than half full, thereby leaving the next smaller electron shell as the new full valence shell. An atom that has an electrical charge, whether positive or negative, is an ion. Let me give you an example. Potassium, for instance, is an important element in all body cells. Its atomic number is 19, and it has just one electron in its valence shell. This characteristic makes potassium highly likely to participate in chemical reaction in which it donates one electron, which is, it is easier for potassium to donate one electron than to gain 7 electrons. So the loss will cause a positive charge of potassium's protons to be more influential than the negative charge of potassium's electrons. In other words, the resulting potassium ion will be slightly positive. A potassium ion is written K+, indicating that it has lost a single electron, and a positively charged ion is known as a cation. Now let's take another example. Fluorine It is a component of bones and teeth, and its atomic number is 9, and it has 7 electrons in its valence shell. Thus, it is highly likely to bond with other atoms in such a way that fluorine accepts 1 electron, and it is easier for fluorine to gain 1 electron than to donate 7 electrons. So, when it does, its electrons will outnumber its protons by 1, and it will have an overall negative charge. The ionized form of fluorine is called fluoride, and it is written as F negative. A negatively charged ion is called as an anion. Atoms that have more than 1 electron to donate or accept will end up with stronger positive or negative charges. And a cation that has donated 2 electrons has net charge of positive 2. Using magnesium as an example, this can be written as Mg++ or Mg2+. And an anion that has accepted 2 electrons has a net charge of negative 2. The ionic form of selenium, or Se, the chemical sign of selenium, for example, is typically written as Se2 negative. The opposite charges of cations and anions exert a moderately strong mutual attractions that keeps the atoms in close proximity, forming an ionic bond. So, what is an ionic bond? An ionic bond is an ongoing close association between ions of opposite charge. For example, the table salt you sprinkle on your food owes its existence to ionic bonding. So, sodium commonly donates an electron to chlorine, becoming a cation sodium plus. When chlorine accepts the electron, it becomes the chlorine anion. With their opposing charges, these two ions strongly attract each other. In this picture, sodium readily donates the solitary electron in its valence shell to chlorine, which needs only 1 electron to have a full valence shell. So the opposite electrical charges of the resulting sodium cation and chloride anion result in the formation of a bond of attraction called an ionic bond. And the attraction of many sodium and chloride ions results in the formation of large groupings of what we call as crystals. On the other hand, water is also an essential component of life because it is able to break the ionic bonds in salts to free the ions. In fact, in biological fluids, most individual atoms exist as ions. These dissolved ions produce electrical charges within the body. So the behavior of these ions produces the tracings of heart and brain function observed as waves on an electrocardiogram or EKG or ECG or an electroencephalogram or EEG. The electrical activity that derives from the interactions of the charged ions is why they are also called electrolytes. Now let's move on to the second type of chemical bond, which is the covalent bonds. Unlike ionic bonds formed by the attraction between a cation's positive charge and an anion's negative charge, molecules formed by a covalent bond share electrons in a mutually stabilizing relationship. It is like the next door neighbors whose kids hang out first at one home and then at the other. The atoms do not lose their gain electrons permanently. Instead, the electrons move back and forth between the elements because of the close sharing of pairs of electrons, which is 1 electron from each of 2 atoms. Covalent bonds are stronger than the ionic bonds. This picture here shows several common types of covalent bonds. Take note that the 2 covalently bonded atoms typically share just 1 or 2 electron pairs. Though larger sharings are possible, the important concept to take from this is that in covalent bonds, electrons in the outermost valence shell are shared to fill the valence shell of both atoms, ultimately stabilizing both of the atoms involved. In a single covalent bond, a single electron is shared between two atoms, while in a double covalent bond, two pairs of electrons are shared between two atoms. There even are triple covalent bonds where three atoms are shared. So you can see that the covalent bonds shown in this picture are balanced. The sharing of the negative electrons is relatively equal as the electrical pull of the positive protons in the nucleus of the atoms involved. This is why covalent bonded molecules that are electrically balanced in this way are described as nonpolar. That is, no region of the molecule is either more positive or more negative than any other. Covalent bonds has also two types, which is the nonpolar covalent bonds and the polar covalent bonds. In chemistry, a polar molecule is a molecule that contains regions that have opposite electrical charges. Polar molecules occur when atoms share electrons unequally in polar covalent bonds. The most familiar example of a polar molecule is water. The molecule has three parts: one atom of oxygen, the nucleus of which contains 8 protons, and 2 hydrogen atoms whose nuclei each contain 1 proton. Because every proton exerts an identical positive charge, the nucleus that contains 8 protons exerts a charge 8 times greater than a nucleus that contains 1 proton. This means that the negatively charged electrons present in the water molecule are more strongly attracted to the oxygen nucleus than the hydrogen nuclei. Each hydrogen atom's single negative electron, therefore, migrates toward the oxygen atom, making the oxygen end of their bond slightly more negative than the hydrogen end of their bond. What is true for the bonds is true for the water molecule as a whole. That is, the oxygen region has a slightly negative charge and the regions of the hydrogen atoms have a slightly positive charge. These charges are often referred to as partial charges because the strength of the charge is less than 1 full electron, as would occur in an ionic bond. As shown in this picture, regions of weak polarity are indicated with the Greek letter delta and a plus sign or minus sign. Even though a single water molecule is unimaginably tiny, it has mass, and the opposing electrical charges on the molecule pull the mass in such a way that it creates a shape somewhat like a triangular tent. This dipole with a positive charges at one end formed by the hydrogen atoms at the bottom of the tent and the negative charge at the opposite end, which is the oxygen atom at the top of the tent, makes the charge regions highly likely to interact with the charged regions of other polar molecules. For human physiology, the resulting bond is one of the most important formed by water, the hydrogen bond. So the hydrogen bonds is the third type of chemical bonds. A hydrogen bond is formed when a weakly positive hydrogen atom already bonded to one electronegative atom. For example, the oxygen in the water molecule is attracted to one another electronegative atom from another molecule. In other words, hydrogen bonds always include hydrogen that is already part of a mole or a polar molecule. Take note that in this picture, the bonds occur between the weakly positive charge on the hydrogen atoms and the weakly negative charge on the oxygen atoms. Hydrogen bonds are relatively weak and therefore are indicated with a dotted rather than a solid line. The most common example of hydrogen bonding in the natural world occurs between molecules of water. It happens before your eyes whenever two raindrops merge into a larger bead or a creek spills into a river. Hydrogen bonding occurs because the weakly negative oxygen atom in one water molecule is attracted to a weakly positive hydrogen atom of two other water molecules. Water molecules also strongly attract other types of charged molecules as well as ions. This explains why table salt, for example, actually is a molecule called a salt in chemistry, which consists of equal numbers of positively charged sodium and negatively charged chloride, dissolved so readily in water. In this case, forming dipole ion bonds between the water and the electrically charged ions, which is an electrolyte. Water molecules also repel molecules in or with nonpolar covalent bonds like fats, lipids, and oils. You can demonstrate it with a simple kitchen experiment. Let's say, for example, pour a teaspoon of vegetable oil, a compound formed by nonpolar covalent bonds, into a glass of water. Instead of instantly dissolving in the water, the oil forms with or a distinct bead because the polar water molecules repel the nonpolar oil. So this ends our lesson for today, which is the chemical bonds. We have three types. The first one is the ionic bonds. The second one is the covalent bonds, and the third one is the hydrogen bonds. If you have any question, please write it in the comment section down below. And thank you so much for watching this video and for listening to this lesson. Until my next video, bye!